And yeah, thanks for inviting me to this conference. So yeah, today want to speak about this joint work with Nikolai Pashenov and Manat Mustafa. So we this is very much work in progress, and we just started looking at some. So we focus on some statements from theory of numberings, and as you can see from the title, the idea is to analyze the strength in reverse mathematics and like reproducibility settings of some statements. Till now we only check some preliminary statement, very basic statements. Possibly something else will follow. So to start, let's define. Let's look at this theory of numberings. So what numbering is in its like generality. A numbering is a very simple object. It's just a surjective map from naturals to family at most countable of objects. Here we wrote subsets of n, but anyway, once you have a family and most countable of, you can first define enumerate the elements. And these numberings are objects, right? We encounter often like daily mathematical life, right? For example, just to have a few kind of concrete examples in the mind to understand which kind of objects are we talking about. So so the family could be. The elements of the family could be formulae for Stoller arithmetic. For example, this is just kind of famous example because it was the first numbering used by Gödel to arithmetize the theory itself. Then we can have as elements of S partial computable functions, recursive models, finite sets, tuples of natural numbers. And indeed, in the classical view of numberings, in classical view of numbering theory, the objects, the family which are usually taken into consideration are a family of whose elements are either like computable or RE objects. So these kind of elements some of them I listed them here, so we see later what does the theory of numberings. But now first let me introduce this generalized approach by Goncharov and Sorby, with which generalized like the classical point of view of numbering theory, because Goncharov and Sorby started like thinking, well, but in the practice, we sometimes enumerate more complicated objects, like sigma n formulae of first order arithmetic could be partial sigma n computable function, delta n recursive models, and so on and so forth. So we enumerate, we may want to think of family, and we do it sometimes, right? About family of objects which are they say admit a constructive description. So they have quite very general approach, much general than what I will tell you now. But so essentially they just say, okay, you once you fix some language, you can if you're able to describe through certain languages. Through a certain language, certain objects, you may want to consider numberings of those more complicated objects. And so they come up with notion, which, as I said, generalized, like the classical view of sigma n numbering, so sigma n computable numbering. So in this case, in their definition of Goncharov and Sorby, they can slice up these numberings, and they say if you take some family of objects, let's say here, let's say sigma n, all objects of a certain complexity, let's say in this case sigma n subsets of the natural and most countable family again, then a numbering is said to be sigma n computable if the relation of like membership into a certain elements enumerated by numbering, the relation between index and a member of this element enumerated by the index is a sigma 0 1 relation. It's very easy, easy, but I think it's kind of easy definition of just numbering, enumeration again, subjective, but lifted up over certain steps for attacking more complicated objects. And those are the numberings we kind of looked at. Okay, so this is just definition of numberings and generalized approach. Then what does the theory of numberings do? Because yes, we use numberings, but what the theory of numberings is about numberings. So the theory of numberings consider these objects like numberings, so fixed a certain, once a certain family is fixed, as look at the numberings and how these numberings of a certain family, because of course you fix a family, then you may have different numberings of the same family. And the numberings looks at how complicated these objects can be and how they are related. Of course, to do this, they introduce some reducibility relation, which is certain, essentially, like many one reducibility between numberings, in the sense that according to the definition of reducibility introduced by Roger, a numbering is reducible to another numbering mu of their numbering of the same family if there exists a total computable function f. And what does it do, this f? This f is such that like the new k, so the elements of the family enumerated by new k is equal to the element to mu of f of k. Just this many one reducibility between numberings. And of course, once you introduce reducibility, you may introduce, as usual, notion of equivalency between numberings. Right, both numberings reduced to the others, one to the other, they are equivalent. And once you do it, this is not hard to realize that this reducibility, of course, is partial order, and it forms for each family. So it forms semilattice. It's called Roger semilattice because Roger introduced it, and is an upper semilattice because the join of two numberings is sup. So generally, in the theory of numberings, the questions they ask and try to answer are questions of the kind of fixing a certain family. Is the semilattice, upper semilattice, a lattice, or questions about other properties of the lattice, and questions about cardinality of the lattice. We're not gonna address such questions and the statements which come from those questions today. Instead, we look at today at certain, let's say, interesting numberings and their existence. Which numberings are interesting? So among the numberings, there are some, these three special: Friedberg, positive, and minimal. When a numbering is called Friedberg, if it is not only surjective mapping, but is also injective mapping. So each element of S is enumerated appears only once in the enumeration. Then a numbering is positive if so the set of pairs which index the same element of indices of the same element is quite simple. Is only CE set. So I can say immediately, so for Friedberg and positive, note that they share a feature, namely they differ, and then the feature is they so to speak, they are internal property of the numbering itself. So they don't mind about other numberings, they just property of the numbering. New is Friedberg if something happens to new, and same for positive. While for minimality, instead is about new and its relation with other numberings of the same family, because a numbering, as you can imagine, is said minimal. To be minimal, it's called minimal if for any other numbering of the same family, if mu seems, if mu is below is reducible to nu, then actually mu and nu have the same complexity. They are equivalent. So what's relation between these two properties? Any Friedberg is positive by definition, because if a numbering is Friedberg, this set here is just empty by definition of Friedberg. And then it also holds that positive is minimal, is not that hard to show this relation. So Friedberg, positive, minimal. So what we I'm going to speak about today are essentially three statements about of the shape, something like there exists a Friedberg numbering, or for any numbering exists a Friedberg numbering, same for positive, same for minimal. Then I will, of course, state the statement once we go there. Before we're going to carry over to our results, like preliminary results. I want to recall this because so in as far as we know, in either reverse mathematics, Baroque, first order arithmetic, reverse recursion theory, this area, there's only one paper, one result about the strength of numbering, of the strength of statements taken from the theory of numberings. And this result is by Whaley, who 10 years ago published this paper you see here, where she considered the strength of this statement. There exists, so you take, I read it. So there exists a Friedberg numbering for the family of all CE sets. This was a statement proved by Friedberg. So the Friedberg that proved first that there exists injective numbering for the family of all CE sets, and then that's why Friedberg numberings are called Friedberg as such. So she look at the statement within as a first order statement. So analyze the strength in sub-fragments of first order arithmetic. So and what she proved is that over a base theory PA minus plus B sigma 2, this statement I read is equivalent to induction for sigma 2 formulae. I decided not to repeat introduction for reverse mathematics, piano, and arithmetic, and whatever, because many people already spoke about it. Whaley herself did it, had a nice introduction on this basic like preliminaries, so I'll skip it, but I just say, so recall, I'm not sure whether yesterday was mentioned, PA minus is just PA without any induction, right? As a base theory, we take PA, we cleaned up of any induction, we add some induction, this bounding principle for sigma 2 formulae, which is just above, just a bit less strong than I sigma 2, and then over this base theory, it is possible to prove that induction for sigma 2 formulae is equivalent to the existence of Friedberg numbering. So let me say just a couple of words for the forward direction, right, from sigma 2 to existence, because it's kind of a reasoning which come up later again. How one can argue that a Friedberg numbering exists. So we take whatever enumeration of all C sets, and intuitively the idea, of course, is just you look at the enumeration, you want to define another one, like a Friedberg numbering, and you just kind of skip the repetitions of the same set. If the set appears first times it appears, you have to place it in the new enumeration, and otherwise, if it appears second time or whatever, other times you just skip, avoid to put in the new enumeration. To more formally somehow to carry over this way of reasoning, you need to argue that for any reset, right, for any set which appears in this enumeration, there is a least index. There's a time when it appears first, and least index meaning it should be the least index I for YE is an index I, such that for any other j, yi is different from yj, of course, right? And precisely I wanted just to point out why I sigma 2 is used in this reasoning, because in this direction, just to argue that for any reset there is a least index, and then once you have it, you have this guaranteed. You define a Friedberg. It's possible to define a Friedberg numbering in kind of easy. Of course, then interesting information also that she proved the reversal, and to do that, you need to. So she show she worked within models fading, like satisfying this base theory, of course, fading sigma 2 induction, and thanks to the failure of sigma 2 induction, the existence of this sigma 2 cuts and delta 2 function from cuts co-finally in the model. She showed that she proved that any enumeration of C sets which is injective is not surjective, so it's not a numbering. That's the way of reasoning, of course, looking at exploiting properties of models fading I sigma 2. Okay, so in her setting, now to finish, like in her setting is very nicely. We can her setting meaning first order arithmetic. Very nicely, one can speak about these statements of theory of numberings, where the family is a family of whose elements are C, right? Because you just speak about their indices and not don't have to look at them as sets, but just as indices. All right, and this can be then formalized in first order arithmetic. But recall that I introduced this generalized framework of Goncharov and Sorby, and we wanted to look at it and look at statements to the strength of statements which appear in that generalized setting. And then to this extent, going like reverse mathematics approach is more convenient because allows to go a bit further than element C sets, because you can speak about sets, of course. Then what is a numbering for us? I mean, what's the problem here? Numbering per se is not second order object. It's actually a function from natural numbers to family of sets. Then we have to call it some way. The very simple way we use, hopefully quite natural, is just look at the numbering as a formula. Indeed, if you recall this definition of sigma n numbering sigma n when well, let's go back because otherwise it could be when, of course, this set of mx x belonging to nu is sigma n. So in this slide, we define a numbering simply as a sigma n form coded by sigma n formula psi xy, meaning that nu x is just the sets of y's such that psi xy holds. Just this. A numbering for us in reverse mathematics. Then we did that definition of numbering and that definition of not only numbering but sigma n numberings for any n. We got back to essentially to this statement, and we formulated this way. So the point is that, so the statement is such: for any for certain reason we get parameters. So for any parameter a and any sigma n numbering with a as parameter in A, there exists a set B and the Friedberg n, sigma n, again numbering with parameter B such that nu and m index the same family, right? So for any sigma n numbering, there exists the Friedberg sigma n numbering, and just the parameter we had that the parameter using the two formulae may change from here through from numbering to the Friedberg numbering. And this it's not hard to show that this statement is equivalent to AC0. So the statement per se from sigma n numbering to Friedberg sigma n numbering, we essentially took it from, as I said, this Goncharov Sorby like approach papers, and try to analyze in this reverse mathematics setting, right? Well, we can look actually at the proof, because as I said, it's not complicated. So let's it's short indeed. So AC first, like the AC0 proves the statement. So to prove the statement, let's take a sigma n numbering. So a formula, sigma n numbering, you recall, is encoded by some formula. So in this case with parameter A, so there is a psi with parameter A, which will hold this numbering. Then, so intuitively, what we, of course, say this is a sigma n numbering. No, wait. So this is sigma n numbering. Okay, this is just a formula. Then what we intuitively know, what we want to consider, and if you think back to this slide of with the least result, is the same idea. We want to consider the least index of the set of least indices of the elements appearing in S, right? Namely, we want to consider the indices indices E, such that the set of indices E, such that for any I less than E, nu I is different from nu E. The two indices they're not pick the same element of the family, right? So this formula, of course, you have to intend this formula as a shortcut for wherein actually one would need to use this psi, right? So this formula, since psi is sigma n, is sigma n plus 1. Sigma n plus 1 with parameter a. But since in AC0 we can prove from A there is A prime, the jump, then actually this is sigma n in A prime. This set is sigma n A prime set. So this means so this means that X per se doesn't exist of course, in the second order part, just A prime exists, but we only look at the set, not as I said, as a set in the second order part, but just through the formula defining it, and this formula is sigma n A plus 1. Sigma n A prime. Then once we have this formula, this is sigma n A plus 1 set, we can, with some induction, which is indeed available, we can enumerate these set, sigma n, sorry, it's not a set, of course, a sigma n set. And then once you have the enumeration, as I said before, you have an enumeration of the least indices, and you can easily produce numbering just using just which only enumerates keeps the least indices of a set and just forgot about the rest. And well, here you can see the formula, so you can check that. One can check actually that this formula, which uses this enumeration and the original sigma n formula encoding nu, encodes another numbering, which is Friedberg, as we wanted, and also is sigma n in A prime. As I said, we change the parameter, and so is what we want, a Friedberg sigma numbering of the same family S. Right, this is all for forwards. Let's go backwards. Again, here the E is simple, and it uses some like idea of building this numbering we define here is taken from is used kind of recurrently in this theory of numberings, and probably gets back to Borel original definition. But anyway, so for AC0 we exploit some result, and as usual there is this. So we have an injective function. We want to prove that the range exists. We define a sigma 1 numbering, and sigma 1 numbering, very simple, because these elements of the family of the numbers we are defining are only either 1 element sets or 2 element sets. So for any x, nu of 2x is either only 2x, nu x is either the family containing only the set containing only 2x, or it can contain both 2x and 2x plus 1 if x is in the range of G. And same for 2x plus 1, nu 2x plus 1, just with the odd and even swapped. And right, thanks to this definition, one can immediately check that you have nice descriptions of nice situation if X belongs or not belong to the range of G, because not belongs to the range of G means that 2x and 2x plus 1, they form singletons, while if X belongs to the range of G, they only appear as 2-element sets in the same set, and they're like both 2x and 2x plus 1 or this pair. Of course, this new is not Friedberg numbering, but now we can apply the statement and get a Friedberg sigma 1 numbering of S. And then thanks to it and thanks to these properties, we can define range of G in a delta 1 way, thanks to this formula, which is like X doesn't belong precisely when this 2x and 2x plus 1 appears as a belongs to two different are enumerated by two different indices, and one can check that actually is correct. Okay, again, going to be easy. We encode 0 prime or the range of some function into Friedberg numberings. So this was about the existence of Friedberg. Then let's go minimal. So for minimal, I recall just well, for notion of for minimal, we need a notion of reducibility. So notion of reducibility, we keep so nu reducible to mu when there is really an index, so a delta 1 function which shows what it should show, that for any k, nu k is equal to mu phi of e k. So minimal reducibility, and the reducting function is really delta 1 even in our setting, right? A very an index an index, a number. Then minimal in this generalized sigma n numbering is minimal if for any other sigma n numbering mu implying nu means actually that nu and mu are equivalent. So here, of course, when one can prove a similar statement for any sigma n numbering, there exists a minimal sigma n numbering mu. And this statement is, you can see, much weaker than the existence of Friedberg. Here again, we exploit some new results, some known result from Balaev-Goncharov, and proof, and just checking the proof, one can understand that this statement, this existence of minimal sigma n, is proved in RC0 already with some bit of extra induction, this sigma 2 induction. And I just say why sigma 2 induction, because Balaev-Goncharov, when they have they take some numbering, sigma n numbering, they wanna produce another numbering for the same family, which is minimal. And this other numbering minimal is defined thanks to membership, non-membership in a maximal sigma 1 set. Okay, here I didn't wrote down what a maximal sigma 1 set is, but so a maximal sigma 1 set is a set which is maximal in which sense? In the sense that for any, if you take any sigma 1 superset of the maximal set, then two things may happen. Either M, the maximal set, is almost exactly the superset, if not for some finite elements. So either M is very big compared to the superset. The maximal set is very big compared to superset, or is the superset, which is giant because it's almost the entire universe, if not for some finite set. There's this duality. So this existence of maximal set, we were kind of lucky because Chong Yang already, they analyzed the statement that exists a maximal sigma 1 set, and they proved that, again, over these, well, here I put RC0, but, well, actually I think for them is PA minus as for these results. So B minus, PA minus plus B sigma 2 over this theory, existence of maximal set is equivalent to I sigma 2. So once you have existence of maximal sigma 1 set, the proof of Badaev control is all like computably computable, some build some computable like stuff on the way, and just uses sigma 2 once more so from having from a set, it's from a sigma 2 set enumeration of it, delta 2 enumeration of it. So there's 2 bits where I sigma 2 is used, and so we got easily this result. What I wanted to say, yes, of course, here there's a question, right? So whether this induction, this bit of induction, sigma 2 induction is really needed or not, or if you want, whether this construction through maximal sets they gave, it's really the way to go, or maybe there's some other construction for minimal sets which doesn't use these maximal sigma 1 sets. So this is still in fact, question, sorry. Then I said we look at Friedberg, minimal, positive remains. So positive are those numberings whose set of pairs of the indices, which are indices of say the same element of the family, is the set is C. So in our setting, we define positive as those numberings for which there is the sigma 1, of course, sigma 1 formula, theta, such that the equality between nu x and nu y is theta. Of course, this should be sigma n numbering, generalized, right? Sigma n numbering is positive, blah, blah, blah. Here we, as we did for minimal, here as well, to keep some kind of absoluteness, we define positive as thanks to sigma 1 formally, and not sigma 0, 1. Just to avoid maybe yes, as I said before, for minimal, to keep some absoluteness in these notions, and to avoid maybe that if you have models with strong parameters, too much things becomes positive or minimal, but one. Then of course, as before, for any sigma n numbering, there exists a positive sigma n numbering. These again, this is 0, and you can get it thanks to the previous statements: existence of Friedberg, existence of minimal, by combining them, and thanks to the fact that any Friedberg is a positive numbering, any positive is minimal, right? This relation between the 3 properties. So that's what we summarizing till now. So we have we look at these basic statements, existence of sigma n Friedberg, existence of sigma n positive, existence of sigma n minimal. 2 are at the level of AC0, 1 much lower. And we can, like, if you want to draw kind of a moral of the story, we can say that there is a separation in terms of strength for these two properties, which are actually internal properties of the numbering, right? As I was saying before, this difference between internal properties, global properties, and global in the sense that the minimal numbering, numbering minimal with respect to all the other numberings is not only about, is not looking only at to itself, and the results is just draw a line between internal properties, existence of like this numberings with certain internal properties, and existence of another like numberings with global properties. Of course, so far we have this picture. In the remaining like few minutes, when we go to quickly to Bayreuth. Why Bayreuth? What we use it for, as usual, so for the usual purpose, one of the usual purposes. So let's get back here. So here I presented this as for Friedberg numbering, right? I presented this as for any sigma n numbering that exists a sigma n, sigma n Friedberg. Of course, very easy. You can think to certain statements like for any sigma n numbering that exists a sigma 1 Friedberg, or even sigma 2 Friedberg, something, right? But let's look at any sigma n numbering that exists a sigma 1 Friedberg numbering of the same family. And it is clear, just looking at the proof, that depending on n, you will need more and more jumps to get from sigma n to sigma 1 Friedberg, because if you have a sigma n numbering, what we need to do to get to a sigma 1 Friedberg is just let this set be a set. And so you can, if you use certain arithmetical comprehension, but if you want to then be more precise, a certain numbers of, or actually for any n would be sigma n minus 1 comprehension, right? You get to sigma 1, and then sigma 1 Friedberg following the same path, not the same reasoning as here. And of course, we just wonder, okay, is it necessary? So is it sigma? Is it, sorry, yes, sigma n minus 1 or 0 n minus 1 jumps really, are they really needed for getting from sigma n to sigma n, sigma 1 Friedberg? And then we use Weyrauch, not for uniformity actually, but just for this checking this repetition of using repetitive use of jumps, right? So Weyrauch, again here one should think how to represent numberings, code numberings in this setting. So this may be definitely not the unique way of coding numberings, and maybe one question would even be how to better code them, how to look at them in this setting of how to look to this sigma n numberings in this setting, suitable for Weyrauch reducibility. So what we decided to do was to code them directly as elements of Baer, And so kind of the idea we use the following. So in reverse mathematics was convenient, like to look at sigma n numberings as a sigma n, or like formally interpreted in a certain way. So in this case, instead we use the other approach of not the other approach, but like Goncharov and Sorby, they say, okay, sigma n numbering, if you have a sigma n formula doing blah, blah, blah. And of course, but then they say, oh, but this is the same as having sigma 1 formula in 0 n, right? So they kind of separate these two parts, sigma 1 part and the strength somehow of the parameter you can use input in the formula. Because it can be more, for them was more convenient to, since the two things are precisely the same, it's just maybe more convenient for like proofs or what they have to do. So here, so we think in this setting, we think a number, sigma n numbering precisely having in mind that is the sigma 1 into something, into 0 n. And we separate so these two parts. So we look at a sequence of where having two parts, like two, yes, being the join of P1, P2 of two elements of where, where P2 takes care of the complexity of the parameter of say of 0 to the n. So it's just a delta n presentation of a function. And instead P1 is the sigma 1 part, so to speak. So it's just P1 for any k. P1k is a triple of two numbers and a string with and these are the usual constraint for what is called oh, come on. Okay, if xy appears at a certain point thanks to a certain sigma, then they should appear again with any tau extension of sigma, the usual, right? Sigma 1 thing. So a numbering then, what a numbering is this represented by this sigma n code, and numbering done like this with these two parts. If so, a numbering is this, you have to read it as nu x is precisely the set of y's such that at a certain bit, certain k, the triple x y sigma, a triple x y sigma is enumerated for sigma of the right kind, for sigma initial segment of the G, whose delta n representation is given by P2, right? So it's interleaving of the sigma 1 part and the 0 n part. So I'm about to finish. So given this presentation of numberings, which again maybe not the best one can think about it. Then of course you can state this Friedberg problem as given as input sigma and code and numbering of an infinite family, and as of course this actually I miss saying in all the other sides, but the family should be infinite. So if you want Friedberg numbering, of course, and the output sigma 1 code Friedberg numbering. And this, as expected, is exactly at the level of 0, and for any n, and we like obtain this strong bar production actually with the usual like benchmark lim, and lim as for any function whose limits exist, give the limit, right? This lim function, and then one consider that it's jumps, and this is known benchmark for this understanding how many jumps exactly needs a problem, and Friedberg, as expected, sits precisely in the corresponding like limb depending on n. So that's all what I wanted to present. As you can see, there are some like already open questions left over, and definitely other maybe statements can be taken from theory of numbering and analyzed, and of course one big point maybe is to look at or to consider other possible representations of number, like coding or representations of numbering in this variable setting, and try to analyze other statements once like maybe once even given maybe various kind of representations. So thank you very much for listening.